Hello? Can you hear me? Oh, good. Okay. Let me get. All right. Uh, just a reminder, the GH section, you'll be meeting at 6:50 in MR 407 North, and GH2 will be Tuesday, tomorrow at 2 o'clock, and GH3 on this coming Wednesday, September 22nd. All right. And the other thing is you need to get the cleared for CLEARED 4 numerical 4 app in order to prove that you have been properly vaccinated or COVID-19 tested negative. So you need to, when you get that app, which they say it will be sent to individual, that you then have to go through whatever procedures they tell you. Okay. Any other questions on these issues? And the other thing is the test number 1 is on October 6th, Wednesday, and it will be live, in that you have to be in person live, even though the exam will be on Blackboard, which would be randomized, but still the college policy is you have to be live for all tests. So the proctor will be there and he will be making sure that you don't talk to each other, hug each other, that kind of thing. Okay. Any other questions before we begin? I can't read that thing too well. Can somebody say what it is?
I was just asking, does that mean it's also open book?
Yeah, basically you have your whole you bring your own laptop, by the way, and the Wi-Fi connection would be excellent for they have been maximized, and you have access to all the whatever notes that you have online, but you don't bring your own. I guess you don't bring your own book along. You just bring your laptop. Okay, and I will explain next week sometime, or just before the maybe around October 1st or October something, the format, the actual fussiness of Blackboard, which is sort of like fussiness of Wiley Plus, but a little bit different. But I will explain all those little fussiness. Okay. Any questions? Oh, I don't have a sample exam, but it would be in the style of the Wiley Plus homework. So all of those homework are really exercises, but I will make it in that sort of context, but will not be exactly the same questions that were asked on the homework, but there will be some that are conceptual, some that are multiple answers that say that, oh, given that I have a such and such and it is at such and such a potential, what is the force acting on some silly point charge? And then you will be able to say, oh yes, that is Monsieur Coulomb's law. And then you will say, oh, you're told that it is so many distance away, and you can figure out. All right. And we will have a review session before then, so before October 6th. And the test itself will be 1 hour 15 minutes. After a 10-minute break, we will resume online course. Even though you're still there, the online course will resume. Okay? Any other questions? Okay, so now I want to kind of like go this chapter 19 to get through chapter 19, and just a quick overview. Chapter 19, we had to introduce or recall what is work energy principle, because we know we have already separated Coulomb's law. Somebody had a question? Oh, how many questions? Oh, let me just again quickly explain. It's sort of like many of the questions have many parts, but they are all connected. So it would be what they call random block. There will be a block of questions on, I don't know, let's say Coulomb's law. And then in it, there will be subparts, part A, part B, part C. And each part I have allowed for 5 minutes for you to look at it. Don't plunge into it. Always look at it in the language that the problem has, you know, that it is a point charge, that it is at this so many meters or centimeters or so many miles away. You look at that and you have 5 minutes to get that done. And then it will be the next question, and you cannot backtrack. It is 5 minutes per question for 75 minutes. That's about 15 questions. So I will have about 15 questions, but it may be like only 5 random blocks or something like that. Maybe 6 random blocks, some random block, maybe only just 2 parts in it. So, and you will have 2 attempts, but each attempt is again randomized. Blackboard is very good at doing that. And it would be such that even if your neighbor is sitting next to you, he or she, her numbers are slightly different than your numbers, and her question number 5 will be different from your question number 5 because they have been randomized. All right, so okay, so now let's come back to this chapter 19, where we met with Coulomb's law, but the people who work with Coulomb's law know that it is too stuffy. What is better is to now separate it into electric field due to your source. Your source is whatever charge, it will produce electric field. And then whether I feel a force due to your source charge depends on my charge. If I have 0 charge, I'll say, what happened? I don't feel nothing. There's no force on me. The reason is my charge is 0. But if I have some charge Q, then I say, ooh, there's a force on me. Why? Because there's an electric field present, and that the electric field is pushing me. And the force is my charge, whatever is my charge, times the electric field. So we are separating out Coulomb's law into the electric field lines and the force on you. And then when you have this separation, you can now begin to talk about what is the work done. Because I am, my charge is Q0, let us say, and then there is a force on me because of this electric field. So then this force on me causes me to go a certain distance. And then you remember from 203, if there's a force on you and you actually went through a distance D, then the force on you did work on you, right? And the work done is the force, which is Q0E times the distance D. That is the work done. And then you can say, where did that work done go toward? Well, you say work energy principle, it goes towards your electric potential energy. Just as you have kinetic energy, I push you along a certain distance, I did this much work, well, you then gain a certain amount of potential energy. I raised this book. I actually had to huff and puff and raise this 10-pound book slowly. I don't want to give it kinetic energy. I just want to give it gravitational potential energy. How much work did I do? mgh. I actually lifted this book up mg by a distance h. So that is the work done, mgh. Where did that go to? Gravitational potential energy. Well, here now we say, hey, there's work done. What is it? It is E, the electric field, right, times Q, your charge, Q0, times the distance D. So this work done, where did it go towards? Electric potential energy. So we then say, I now can understand, define a new thing, which we call electric potential energy. And then the people in the field say, yeah, that's a good idea, good concept, but it is actually more easier to now think and introduce this thing called potential energy, V, electric potential, and just call it potential, electric potential, that this charge now is at a higher potential. And when you pushed me from this side to this side, I gain electric potential energy. And then you now say, whoever's on this side, whatever is your charge, per unit charge, this position here is now at a higher potential. When you have a battery, when you have a car battery, then you say, hey, the anode, which is the part of the battery that has all the positive charges, right? The anode is at a higher potential. And if I now were to connect a wire from your anode to your cathode through some circuit, then my electrons or my charges inside this wire, or they will be running from your higher potential to the lower potential. And so that is now an idea of potential. You now say, I can think of the potential. The electric potential energy is your charge Q0 times this potential. And we will now introduce language called potential. We call it the electric potential. And then that potential for a point charge is KQ over R, where K is the Coulomb constant, the one that is like the Newton's constant. And it numerically is 8.988. I think for most of the book, it just uses 8.99, but that's okay. The people who are engineers and scientists, they actually know it to 10 significant figures because it's a very important number. But it is in these metric units, in the system international units, it's 8.9, let's say 8.99 times 10 to the 9. And in the metric units, since we now introduce this unit called volt, then it is volt meter per coulomb, where volt is named after Voltaire. All right, so the concept is that now I can look at what is the potential. You have a charge plus Q down here, then it produces potential at all the distances, at whatever distance R. If it is here, then the potential around it at the distance R is KQ over R. Now, if it is further away, it is at a further distance, then it is at a lower potential. The potential is very strong near this charge. When I come close to you, man, I can feel that the electric field is stronger and the potential is stronger, right, higher. And now they also now introduce this language of what you call equipotential service, meaning that all the points at the same distance R, they have the same potential. So we call that equipotential. And all the points that are along this, that are at a distance big R from the center, that is also at an equipotential, even though that potential is lower than this potential. All right, are you seeing this picture? Because we will be using that picture a lot for concepts. And now the other thing you can see just by this diagram, this is at a higher potential because you're closer to the point charge. This is at a lower potential. Which way is the electric field? Since this is plus Q, the electric field is from here towards there. So the electric field points from a higher potential to a lower potential. You got the picture now? The electric field is from a higher potential to a lower potential. When you have what we will later come across, this thing called capacitor, two parallel plates. If the two parallel plates, one side is positive charge, the other side is negative charge, then the positive charge, the plate with the positive charge, is at a higher potential than the negative charge, and the electric field is pointing from the higher to the lower. Am I going too fast for you? It's the language. I hope it's the language that you grasp, because in a certain way, that language has now permeated all of our daily life. I have my my phone. I need a charger. Well, then I need a battery to charge it. And when they say, "Oh, what is your battery?" you then say, "Oh, it is a 6-volt battery," or it can be a 12-volt battery, or it can be 110-volt battery, 220-volt battery. The language of potential has now become a very important concept, because that's how you get my electricity. Con Edison, they actually have a generator, a plant that actually produces electrons, charges that are now at a higher potential. That's sort of like you have a plant that actually was able to boost up the potential to 675,000 volts. Very, very high potential. And then because of that high potential, and on your side, you are, very low potential, then there is a big electric field that pushes all these electrons, zoom, down the transmission wire. And it can come all the way from Niagara Falls, where it's been pumped up to 675,000 volts. And now it comes across, by the time it arrives outside New York City, it may still be about, I don't know, let's say 600,000 volts. And then they step it down and step it down and step it down, so that finally when it comes to your apartment, to your building, to my house, it is at 110 volts. The reason is I wouldn't want to have my power supply come into my house at 600,000 volts. If ever there is any leakage in my circuit somewhere, I touch anything, I will be a gone case. And so they need to pump up the voltage high. We will come to later all this thing about resistance, about ohms. You raise the voltage, and then you send it across the transmission line, and then you lower the voltage, so that in the end it is more or less safe for it to come into your house. For the phone chargers, you don't have to worry. It is so many small volts. Maybe it's 3 volts. For these AAA batteries, I don't know how many volts it is. 3 volts, 4 volts. So that's because the equipment that we are using, they don't need high voltage. And in fact, for a lot of these new uh, gadgets, what Internet of Things, for all of these little things, now the voltage they use are so small, and it is a different language altogether. They call it nanotechnology. But anyway, what I wanted to sort of get into your understanding is this concept of equipotential, that this is at a higher potential than this. And from the higher potential to the lower potential is the electric field. And this electric field now will be an important thing because you measure the potential difference, and you can therefore know what is the electric field. And the electric field depends on the distance between, the voltage difference. That is the relationship which we will come to. Am I going too fast and too high for you? Okay, we will see this again and again and again, but I just want to introduce you to this picture so that you have it first in your mind, that there is this thing called equipotential surface, and the surface that is closer to, excuse me, the surface that's closer to whatever is your source charge is at a higher potential, and the electric field goes from higher potential, excuse me. I'm glad you are not in my presence because I don't have a mask on. But yeah, thank you. Okay, so now let's go on. Gee, what am I? Yeah. Well, I have basically already gone over this. This is high potential, this is lower potential, electric field line. So I have basically been going over it. And now this is for those engineers. They didn't say, oh, you have this, and then you can trace all the electric field lines. Don't worry. From now on, I will always put a green sign as a warning that you are not responsible. Leave it to the engineers. Now this is what we want to sort of get a sense of. This is what you call a capacitor, or let's say a battery. And on one side is positive charge, it's been charged with a certain amount of charge, Q. And on the other side, it is minus charge. That's why the electric field is from positive towards negative. And this is the electric field. And this is the equipotential surface. And this equipotential surface is closer to this. So this is at a higher potential. This is further away from this, so this is at a lower potential. The electric field goes from the higher potential to the lower potential. Do you see now what I'm using the language? And now this slide is to say, what is the relationship? If indeed I know electric field is from here to here, and I know now this parallel plate capacitor has a distance, or this book right now calls it delta S, is some separation, right? If there's some separation, what is the relationship between this E and the potential difference? We know this is higher potential, this is lower potential. But if I know the electric field, because I happen to know more about this side by Gauss' law, we will come back to Gauss' law. Since I know what is the electric field and I know what is the separation, can I now figure out what is the potential difference between here? Is this a battery whose potential is 12 volts, or is it 15 volts, Or is this a big capacitor that is 240 volts difference? Is there a relationship? Is there a direct relationship between the electric field, the distance or the gap, and the potential? Well, I will now quickly recap what I have already said, and I'll say, hey, I remember my work energy principle. And then work energy principle says, if I go from A to B, there's a certain amount of work done, and I take my own charge, Q0. Q0 has nothing to do with this. It's just my charge. And I happen to have a charge, because if I have no charge, no work is done on me. So I jump into between these two plates, but I have a certain charge Q0. Then I feel a force. What is the force? My charge Q0 times the electric field. And then the work done? Well, your electric field pushed me, right? Your electric field pushed me this distance to go from here to there. Therefore, the work done, I remember from 203, is the force Q0E times delta S, right? But then I also remember work energy principle. Where did that work go towards? Well, from 203, you say all of that work went towards the electric potential energy. My electric potential energy. I have a charge Q0. I now will have more electric potential energy because you pushed me. You did this much work. This electric field forced me. You did this much work. So my electric potential energy increased. Well, I can now write the electric potential energy is related to what we call volt potential, electric potential, by whatever is your Q0. All right. The electric potential is electric potential energy per unit charge, Q0. So I go back to the relationship between the electric potential energy and electric potential. It is just Q0. So you did this work on me. I have charge Q0. Then now I will have a higher electric potential. I have a higher electric potential energy. And I can now re-express this as I can divide out the Q0. Q0 is in a way irrelevant because I'm interested in the language, the concept of you are on this side of my battery. You are at a higher potential. If I ever connect a wire across from this side to this side, man, it will send a current through. Why? Because you will force all the charges inside my wire to be going from high potential to low potential. So I now will be able to write now this answer, which is that the electric field that is in this capacitor or in this battery is the potential difference, Vp minus Va over delta S. All right, it's Vp minus Va over delta S. And this is from a higher potential to a lower potential. And this then says that, well, actually, the sign gets a little complicated because delta S in this language is XB minus XA, and XB minus XA and VB minus VA. Well, don't worry about the sign, whether it's plus or minus. It is potential difference divided by the distance. That's the electric field. And so this now is the working it out, and now they say that the potential VB minus VA, this is at higher potential than this, so therefore the delta V or the VB minus VA is negative because this is at a higher potential than this. And then the potential difference is -3, the distance is 0.03, and they work it out that the potential, the electric field strength is such and such. Excuse me, I better blow my nose. Sorry. Sorry about that. Is this more or less okay with you? The concept of the fact that when you have a parallel plate capacitor, one side is at a potential and the other side is at a lower potential, then there will be an electric field from the higher potential to the lower potential, and you can actually relate the strength of the electric field to the potential difference depending on your distance gap. That's this gap. And the magnitude is E is equal to V over D, where V is the potential difference. But now we need to do a little bit more, because most of the time the batteries or the capacitors, they are not empty separation. In other words, it's not empty space. It's not like you have a anode and a cathode and with nothing in between. In actual fact, for a battery, it is an anode and a cathode, and in between is some dielectric, I guess I'm not a chemist, but they have some gel in between. And the manufacturers of all these battery cells, they know what kind of gel to use, right? They call them dielectric. So most of the time, we are not dealing with pure Coulomb's law because pure Coulomb's law is in empty space. I have a source charge. The force between this charge and this charge is Coulomb constant K, Q1, Q2 over R squared. But here now, we're dealing with some, gel dielectric material in between your cathode and the anode. And so we need to now get into a more interesting concept. And that concept has to do with what is a dielectric and how does that affect the relationship between the electric field strength and the potential difference. All right. And now we already kind of can see that there is a relationship, but to figure it out, I now will go through a certain concept. And the concept that the users need to have is, I have a certain charge. My battery, my phone charger, they can give me this much charge to my phone, Q. And you tell me that you want the voltage across to be, let's say, 10 volts or 6 volts or 4 volts, then there's a relationship between the charge and the voltage, and that is called the capacitance. What that means is, I have a battery, and it is a 6-volt battery, but if my 6-volt battery has more capacitance, it actually has a bigger charge. Therefore, I can charge my phone and it can last for, hopefully, 24 hours. So if I have a charger, which is a capacitor, that has a higher capacitance, then for a given voltage that it has between the cathode and the anode, it can give me a phone that can last longer. Did you follow this language now? We are sort of like evolving on the set of language. When you have a laptop, whether you have, I don't know, iPad, or whether I have a Surface, I have this is a ThinkPad, Lenovo ThinkPad, whatever is your laptop, there is always the issue. How long does the battery last? And it's very irritating if you have a laptop whose battery, when it says fully charged and it only lasts an hour. Well, it's not long enough for your taking an exam. But if when it's fully charged and you're using it in a normal way, not by downloading videos and playing games with it, and if it lasts for 3 hours, good. Better if it is lasts for 10 hours and so on. So this capacitance is a very important thing for users, for manufacturers, because they are going to sell you a laptop and they'll say, see, now your laptop can last for 3 days. Of course, you have to pay more if it can really last that long for voltage of such and such. Are you okay with the language? The language is evolving, getting more and more higher concept. All right. And now the capacitance is this proportionality constant, and the unit is farad. The unit is coulomb per volt, but it's been given a name farad. And I want to sort of always step back and say, what are these units? We know Coulomb has to do with Coulomb having investigated the Coulomb's law. But who is this farad? Well, this farad, later you will find, is Faraday. And this is a very big name in electromagnetism study, because all of the induction with solenoids and everything, you will find later is related due to this Michael Faraday. And for the moment, we don't need to go into his background, because we will be coming back to Faraday's law of induction. And just to now mention, when you have a empty space, which, as I said, is not the usual batteries, the usual batteries have some dielectric, whether it be some kind of gel or whatever is the dielectric, there's a difference. If there's empty space, whatever is your electric field coming from this side, it is positive charge, the electric field will just go straight across. All right. Near the edge, there may be some bulging, because after all, it can go out and then come back in, it can go out and come back in, but in between, it is all parallel to each other. So there is a certain electric field when it is empty space. But now you put in a dielectric with a certain dielectric constant, and the engineers will tell you, if you use Teflon in between, the dielectric constant is 2.1. If it is ruby, it's 5. If it is water, it is 80. If it is methyl alcohol and so on, the dielectric constant, they measure it. And it's important to them that they can measure it. But what we want to now sort of figure out is, what is the difference by our knowledge of the language? So here now I want to go through capacitance of a parallel plate capacitor. And I will go back to this original one. Original one we can say, hey, I know that by Gauss' law, if you vaguely remember Gauss' law, do you remember Gauss' law? Gauss is the other mathematician who is also important for physics. And he just simply says, oh, I know each one is a source of electric field. And if I now take a surface, what they call a Gaussian surface, I can then say that the net flux, electric flux coming out of that surface is the charge inside Q divided by epsilon zero. Epsilon zero is related to the Coulomb constant. Well, if you now go through that, if you go back to the slide that has Gauss' law, you'll find that inside there is no electric field because this is a conductor, and in the conductor all the charges go to the surface. So inside there is no electric flux. Then this side of it, the flux is zero. Why? Because the electric field is parallel to your surface. But over here, the electric field is perpendicular to your surface. And so indeed, the flux will be the E times this area. So therefore, it is the total charge divided by epsilon zero, and it is Q over, that's the surface. The total charge inside is Q, and per unit area. So if my area is big, then there would be a bigger flux, but the flux is then E times A. E times A now is related to the charge Q. So this is then the formula for E is the surface charge density Q over A divided by epsilon zero. This is the situation when it is empty space. And incidentally, the engineers, the scientists, they call this permittivity because later on, when we deal with Faraday's law and electromagnetism, we would also meet again with epsilon zero, permittivity, and mu zero, which is permeability. But anyway, those are language issues. For the moment, we just simply say Gauss' law taught us what is the electric field, and is related to the charge inside, and the flux is electric field times the area, and is equal to the total charge inside. And so you have electric field times area, that's the flux, which is related to the charge, so Q over epsilon zero. All right. So the total charge on this side is the area times E zero, and it is multiplied by epsilon zero because the total electric flux is AE, and it is by Gauss' law Q over epsilon zero. But now we recall that if this is the gap or the distance between these two plates, if D is the distance between the two plates, then E0 times D is the work done per unit charge, and therefore that is the potential drop. And therefore you now say, instead of writing it this way, I can now write this as Q as epsilon 0A divided by D times V. So that I now can introduce this concept of capacitance. I want to have more charge so that my laptop will last longer, or my whatever that I use it for is I am able to charge my phone with a more charge in it. Then this C is the proportionality called the capacitance, and this capacitance is now epsilon 0 A over D, because I look at this. From Gauss' law, I figured it out. Therefore, I now know this is the capacitance. All right. Now, Having introduced this language of capacitance, that is the proportionality between how much total charge you have in your battery, given the potential of so many volts. Now that we have this relationship, we now want to say, what happens if I put a dielectric in between? What do I mean? That means I put some material in between. But this material itself has, molecules and atoms inside them. And this molecule and atoms inside them, they will now be sensitive to your electric field. Well, if you have now electric field, and I have now electric field, the electric field, some of them now will land on this side. Why? Because my atoms inside this dielectric, they will have plus or minus. And the fact that you have an electric field outside, then those inside will say, "Ooh, I am negative charge. I like you." So those that are negative, they come to this side. And then the positive ones, "Ooh," they say, "I hate you." I go to this side. And so it becomes plus minus, and then plus minus, and plus minus, and plus minus. So that in the end, what I find is some of the electric field lines don't go across to the other side. Instead, they end on this dielectric, this face of the dielectric. You see it here? They end up here, and then those that are the opposite of this, they are on the other side of the dielectric. They then become the source to end up over here. So now some of the electric field lines don't manage to go across, but some do. So you now find that the electric field inside this dielectric is smaller than the electric field that is in the empty space. Are you seeing this picture?
Yes.
Right? And you have to grasp that very well, right? You say, oh, when you now, put a dielectric, whether it is some kind of gel or whatever, the people who are chemists, they know how to do it. Well, then what happens is not all the electric field lines shoot across. Some of them land over here, land over here, land over here, land over here. Only some manage to go through. So that now my E, that actually I can now measure inside this battery, inside this capacitor, is now smaller. It's E0 divided by kappa, and kappa is called the dielectric constant. Remember the previous slide? The engineers have figured out that kappa is, I forgot what, for water is 80, and then for this glue and that glue, it is such and such. But the main thing that we need to grasp is that the electric field, the actual electric field inside this dielectric is smaller. Okay, now if that is the case, we now go through the Gauss law again. We now go through the Gauss law and we say, well, if I take a Gauss surface, what is the net charge inside this? It's no longer the original Q. I know I had a little Q that was, so many coulombs. But now it is less. Why? Because my dielectric kind of like, this was all negative, but now I have some that are positive, so that my net charge now is less. It's the original Q divided by kappa. All right? And the Gauss law says, oh, I can now figure out the actual electric field in terms of the surface charge. But the surface charge now is smaller. I call this capital Q. The book, I'm using the notation of the book, so This capital Q does not mean that it is bigger than the original. It is actually smaller. So now this is the new Gauss law. Let's say that I take the Gauss surface and I want to measure what is the actual electric flux in between in the dielectric. It is now smaller because this E is smaller. And I now can write this in terms of the original Q. Because if this is what it actually is in the presence of dielectric, but I am more interested in, I actually put so much charge on this battery, because that's the one that will now cause my current to flow. When I connect a wire from the anode to the cathode, it is these Qs that now would be running around. So I want to know what is the relationship between my original Q and your electric field in the presence of the dielectric. And so I have to now come from here and re-express it in terms of this original Q. And then remember that work energy principle tells me if this is your effective electric field, then the work done is E times this distance d, or the gap distance d, and that is the potential difference between this plate and that plate in the presence of dielectric. So when I re-express this, then the total Q on this plate, which is what you had already put in my capacitor, is now related to the potential difference V between this plate and this plate by this formula. And the capacitance now is kappa epsilon 0 A over D. What that means is that when you have a dielectric, your capacitance increases. By going into Gauss law and so on, the net result is if you now put between my original empty space parallel plate some material, dielectric material, then my capacitance increases. My capacitance increases according to the dielectric constant. All right, so we now have come to understand more about the various batteries or appliances that you want to have a bigger capacitance. Why? Because you maintain a potential difference overall. I maintain a potential difference of 6 volts. But when I am using 6 volts, because I use a dielectric in between, hey, my capacitance is now 100 times yours. And because my capacitance is 100 times yours, my charge that this laptop, that this whatever capacitor can have is now so much more that I can now use it to play games, or not play games, but do all of the internet courses and so on for a longer time. So this is therefore a very important concept, that indeed you can increase the capacitance according to your dielectric constant. All right, now you don't have to remember how to derive it. I hope I'm not making you, get a little bit groggy to how to derive it. It's not the derivation, it's the concept that indeed you can have more capacitance if you now have a dielectric with a high dielectric constant. And that is always the important thing for applications. Any questions? I hope you can follow the picture. No questions? Okay, no questions, right? Yeah, so far. All right. So now we now come to a conceptual. And now it's an interesting conceptual question because it goes back to what we mean. An empty capacitor, right? We started with an empty capacitor. It's connected to a battery and charged up. So the battery charged this up and then they remove the disconnected from the battery. What that means is that therefore you manage to deposit this much, plus Q and minus Q. All right. And now you put dielectric material between. And then the question becomes, now you got to think a little careful here, right? The question becomes, does the voltage across the plates now increase, remain the same, or decrease? Somebody, what was it now? Can somebody say what is it? Increase or decrease or remain the same? There were
I said it
some,
increased A.
that the voltage increase, because that's the question, you see. Does the voltage increase? I don't know. Somebody, maybe I should have used a poll, but anyway, the polling takes too much time. You follow, you have to look at this, all right? Stare at it and say, Q, does Q change? No, Q was whatever the battery charged it to be, right? Q didn't change. But what did change is you increase the capacitance, right? How? Because you remember how this silly professor went through, half an hour of explanation. The capacitance increased, but Q did not increase. So what happened to V? Huh? Increase or decrease? Decrease. So as a result of your having a bigger capacitance, your voltage across here actually decrease because your Q remained the same. You didn't move it around. And then you know what the people do? I mean, the engineers, they are smart, They say, yeah, true. My potential volt is smaller. But what they can do is now to make the gap smaller, right? After you have charged it, hey, you can move the plate, the gap smaller, right? If you move the gap smaller, even though the dielectric constant is, let's say, 80, but if you move this smaller, your voltage will not decrease so much. You follow what I'm doing? In other words, you realize you're the engineer. You say, hey, I first charged this and it was, so many, let's say, millicoulomb or microcoulomb, whatever the unit associated with a battery. The battery is not one whole coulomb, but microcoulomb or millicoulomb. So I have already charged it. And then I say, I want to increase the capacitance. So I now put in the dielectric. But then when I put in the dielectric, the potential drops. So what do? These engineers, they are not, hired because they don't know the principles. What they now do is they make the plate, the capacitor, what do you call? They squeeze the capacitor. All right. Now, if you now squeeze the capacitor, you now don't lose so much in terms of potential, because even though the capacitance has, the dielectric constant has gone up, you now make D smaller, No, what am I doing? What am I doing? The capacitance has gone higher, but what I do is now I increase the distance. See, I'm not an engineer. Don't hire me as an engineer. All right. You follow what I'm doing? I'm playing with this basic formula. This concept question says that if you do nothing else, the capacitance increase, but your voltage decrease. But to compensate for that, what you do is you now make D bigger so that then your voltage remains the same. For example, anyway, there's a lot of engineering tricks involved with capacitors, so I won't. I'm not an engineer, so. But you get the picture here, the end result of this conceptual question. Okay, and now just a quick. Sorry, what was that? Can somebody read that question?
So
What was it?
capacitance decreases, which makes the voltage increase.
No, if you now, you already put in the dielectric, so kappa is a big one, and now if you decrease the gap, actually it makes your voltage even smaller. But now there are some applications where they don't need high voltage. For some of these gadgets that you have, the voltage is small, so therefore it does not matter. You can indeed start with a dielectric constant kappa of, I don't know, let's say 20, and then you make this D smaller, then this C increase and the voltage decrease. But your original voltage that you use the battery was 12 volts. But what they need for the gadget that you have somewhere inside your laptop, they need these gadgets. Their voltage is smaller, much smaller. So it does not matter. What is important is that you have increased the capacitance so that it can actually have this much charge. So it is all a question of what is your end result. Your end result, if you want the end result for the actual voltage across your final capacitor to be, millivolts, or then you just say, and I only use a dielectric constant of 4 or 5 because it's the material that I use, then I can now decrease D so that my final voltage is now millivolts. Are you following? It's all a question of what is the application you have in mind. And the application, in the end, the voltage for your application may be millivolts. What is that? What is A in the equation? Oh, A is the area, the cross-sectional area of your thing. And that also is variable. The chip that you use inside this computer when you open up the laptop, right? The chips, all the area is small. These chips, the chips themselves are like capacitors, and that area is very small. So you're playing with kappa, depending on the material. You're playing with the size of the chip, A, and you're playing with the size of the thickness, D. And the engineers, they have a lot of fun in playing with this. Now, in fact, the next slide actually shows the kind of fun they use. We have a laptop, and we all have a keypad. Now, I'm not an engineer, but this is what the book reminds us or shows us. that this itself is a capacitor, you see that when you press on it, when you press on the key, then you are squeezing the capacitor. Here's the capacitor, and you are squeezing the capacitor. Here's the little underneath each key, like Z and X, C, V, and so on. Each one, there's a plunger, and when you press on your key, you are pressing on the capacitor. And when you press on the capacitor, you are now changing the D. The A is fixed, but you're changing the D. And because you're changing the D and the dielectric constant is fixed, then you are varying the voltage. And the whole circuitry inside this keypad is that then it sends a signal to the rest of the computer that says that, hey, my friend just typed a X, or just press on C, or just press on F, and so on. That is what that whole formula is so useful. They are playing with this. Kappa is fixed because whatever the material they use. A is also fixed because the size of your chip. What they play with is D. And when you change D, you change V. And so because you change V, the circuit inside this computer now will say, yes, somebody typed 1, or somebody typed 7, and so on. Do you see now? And it's all having fun with this formula. And what we have, so to speak, struggled with is to get the concept straight, and then we leave it to the engineers to have fun with it. Okay? Any questions? Is this picture clear?
Yes.
Yeah, it's a very neat picture, and it gives you, in fact, the kind of fun, well, not fun, but that's what all different, companies, laptops, and there are some people who are able to have a laptop that's very thin. You know, right? Nowadays, the more money you pay, the lighter is the laptop. Well, then their thickness now is getting smaller and smaller. And now they have to now say, hey, engineer, you better find the right dielectric, and then make sure that it is such and such. So they I wouldn't say fool around, but they play with just these formula. Okay. And here is some examples. I leave it to the engineers to work it out. Okay, one last concept, and it's maybe not that important for you and me, but for the engineers, again, it's important, is how much energy is stored in the capacitor. Well, the formula, again, leave it to the experts. It's 1/2 CV squared, where C is the capacitance and V is the volt, your voltage. Your capacitor, the voltage across the capacitor, then it is 1/2 CV squared. How they derived it, we can leave it to the engineers. But the formula that you may be, at least know it, is that it is again related to this key concept of the capacitance and the voltage across the capacitor. And clearly, the higher the capacitance and the bigger the voltage across, then the more energy is stored in there. And for the power company, when they have things like a solar panel, or they are interested in how much energy is stored inside this solar panel, how much energy is stored in this capacitor, how much energy is stored in this plant, you can think of this plant as a capacitor now. And if the voltage across this plant is, I don't know, such and such, the energy is what they call millions of joules, and therefore the power associated with it is megawatts. So again, the engineers, they have a lot of fun. Well, let's say they have a lot of parameters to play with to figure out how much energy there is. We leave it to the engineers. We just know that there's this formula. And here I will end with some biomedical applications. Not that I know how they do it, but it is important because in biomedical nowadays, you do a lot of analysis, right? And you want to measure what is the pulse. You want to measure what is the blood flow. And in all of those, what you're doing is you're measuring the voltage, you're measuring the current that flows. And there are these applications, I don't know it myself. There is your nerve endings, you have whatever axon, cell body. Don't ask me how do they do it all, but I know when I go for electrocardiogram, they actually, do I have a picture of that? Yeah, they actually put, all these probes down here, right? I don't know, they call it A, B, C, D, E, with the legs and then near the heart in order to figure out your EKG. And all they are doing is to measure the amount of current that flows. Electrocardiogram, right? Now, it's not important for us because we are not the people designing the machine, right? But what's important for us and for you is to be sure that you didn't misidentify the wires, right? I have always wondered when the nurse comes by and puts it on this side and that side, is she paying attention that, A goes to A, B goes to B, C goes to C, D goes to D? Because if not, whatever signal they get is all wrong. Only if it is the correct way, then you'll be reading the potential difference from this side of the heart to that side of the heart. All right, so we leave it to the engineers, but we do recognize that the measurements are measurements of the electric current that is flowing, and they can now measure it. What is this now? This is electrodes connected to detection of your brain. They can also measure the brain waves. I have no idea what is normal alpha rhythm and what is abnormal. Does anybody know this? I don't know. Have you, in your, do you have labs in bioscience that deals with these devices? But all that is important is that when you are given this device, you better follow very well the procedures that the manufacturer tell you, that you connect this to here and connect that over there. And what you're reading is probing is the brain wave on this part of the brain. And then there's a big difference between this part of the brain to this part of the brain and to this part of the brain. What do you call it now? Pure and impure waves. Yeah, I don't know the language, but there is, which is why when you go for EKG and for ultrasound and those things, there is a technician who actually reads it, and then the technician has to then analyze it and send a report to the doctor. And then the doctor then tell you, oh yes, you have abnormal something, AFib. They can measure your AFib, they can measure your valve, because the equipment are so sensitive now that they can measure all these. You leave it to the engineers who have actually been so much involved. And in this, in the future biomedical science, there is more and more equipment that are meant to help you monitor. Like I'm told, some of these Fitbit, they can measure your, what is it now? Not just the number of steps, but also, what is it now? The blood flow. You know, they can measure the blood flow without jabbing it. And that has to do with they know very well the resistance and the way a pulsing vein, how it affects the skin. I don't know. I have heard it somewhere, but I'm not an expert on that. Okay, I think we can now say that we are done with chapter 19. Okay. Oh, and just a quick. Didn't we already do all this? Yeah, we did all this. I guess this is just a review of it. Oh, I have already done review. Oh, how come this is now going back over everything? Well, okay. I think it would be good now to go to chapter 20. All right. So let me. Okay, now let me now go here. Can you see it now? You can see
Yeah.
it, right? Okay, it's okay. It's now we need to go to chapter 20 because we've been dealing with these fundamental concepts of what is the electric potential, what is the capacitance, but at some point we want to connect them so that actually a current will flow. So far, all the things that we are talking about are sort of like static. You have electric field. Ooh, I feel a force due to this electric field. And the strength of the force is my charge, Q0 times whatever is your electric field. And maybe as a result of that, I will gain electric potential energy. And therefore, I figure out what is the relationship between the electric potential versus the electric field and the distance d. Now, in chapter 20, we want to actually go into applications where I connect them. So this you call them electric circuits. Well, in electric circuit, you have an energy source, an energy consuming device. They're connected by conducting wires. So here is your battery pack, and you now connected by wires. And then the wires actually are a lot of electrons. Today we know it as electrons. And electrons are now the ones that are zipping along. When Benjamin Franklin gave the convention that positive and negative, well, he did not know that the things that actually move were electrons. And so he says current flows from positive to negative. But actually it is the electrons that flow from negative to positive. But the current is still positive direction. It's just that now it is the electron that has negative charge going in the opposite direction, but it is still the same positive current. Anyway, the language stuck. And so we all now say, this is a positive current that flows from positive to negative. It is not positive charges moving. It is actually electrons moving opposite direction. And what we now want to have is to say, I have a positive terminal and a negative terminal, and I would now want to connect. Like, for example, my car, my battery went dead, and now I need a booster. And now my friend comes along with a booster battery, and then he will connect his positive end to my positive end and connect his negative end to my negative end in order to boost so that I can start my car. When you have somebody helping you, never connect his positive terminal to your negative terminal, and your don't cross wire, because if you cross wire, you are destroying, you're short circuiting his battery as well as your own dead battery. So when you are connecting to help your friend, make sure that it is you connect your positive end to his positive end, and there's a color code associated with it. I think it's red for plus. Is it red for plus? Anyway, here they show you, right? So it is you need to know that anode is the one that is positive and it has a raised button, whereas the cathode is the flat button. Well, when you connect whatever circuit, when you connect and now a wire, your currents are flowing, then there will be charges moving per unit time. And now let's continue to follow the convention by red and black. Red for black, what was it now? Red and black, yeah. And red is for positive or negative? I don't know. I'm getting old. Huh? Red is for positive. Yeah, that's sort of, I vaguely remember when I have to. Okay, so now let us just follow Ben Franklin and say that current is positive charges flowing, although in actual fact it is negative charge moving the other way. Anyway, so now we want to define something known as the current. Current is when something is actually flowing, and the current, which we use I. Now, I don't know the historical reason why the current is called I, but I guess you cannot call current C because C already is used for Coulomb, the charge. Anyway, current I is delta Q over delta T, the rate at which my charges are flowing across. If in 1 second I have 10,000 coulombs passing by, man, the current that is flowing is 10,000 amps. All right, 1 coulomb per second equals 1 ampere, 1 amp. The current that flows in our battery that you use is not 1 amp. It is microamp. But the unit, the metric, the SI, the System International unit for current is ampere. And I downloaded a picture of André Marie Ampère, a French physicist, engineer, who lived in the 18th century. And I also downloaded from Wikipedia, because it's interesting to know, when you are dealing with these, that he is a physicist and mathematician. And he is very important because he helped found classical electromagnetism, which he referred to as electrodynamics. So Ampere is a big name for amps, and Faraday is another big name, but we will come to Faraday. And he is, namely this Ampere, is the inventor of numerous applications such as the solenoid. And we will learn about solenoid when we come to Faraday. And the electrical telegraph. Well, today, of course, people don't use telegraph. They use Telegram, and Telegram has become a app nowadays. But anyway, so these are the fields that he did. And then I was most interested when Wikipedia says, as an autodidact, Ampere was a member of the French Academy of Science. And I say, wait a minute, what is this autodidact? Does anybody know what is this autodidact? It sounds very high class. Anybody know? Self-taught. Yeah, wow, boy, I'm impressed. I never knew. This monsieur, yeah, this monsieur, Professor André-Marie Ampère, he taught everything himself. He did not go to school. He actually learned or taught by himself. So he's a self-taught, and he is a member of the French Academy of Science and professor at École Polytechnique and Collège de France. And this electric current is named Ampere. And his name, I was so interested to know, his name is also one of the 72 names inscribed on Eiffel Tower. I don't know other names, but maybe someone. I mean, if you go to Wikipedia, you can click on it and you can find out all the other names. But it's Ampere is an impressive person. Okay. All right. Now, when you're dealing with currents, we now have to come back to overall concept that there's a current flowing. There is a difference between what we call DC and AC. That has to do with how the current is generated. But DC is where the current only flows in one direction at all times. It is all these electrons flowing in one direction, or in this case, we are assuming these are positive charges going in this direction. So it's the DC current. When you have a solar panel and you have a panel and you now convert solar energy to electricity, the current that comes out of it is DC. Because the energy comes and is absorbed, and this is like a capacitor down here, and it only converts to a given potential difference, so it is a DC current. The current that we get from Con Edison in New Jersey is PSE&G, Public Service Electric and Gas. The current we get is alternating current, because the way it is generated is by Michael Faraday. By induction, you have something going across the loop across a magnet, and by the electromagnetic induction, the current that is induced when it is in one direction is positive. Then when the grid, or when that thing now turns over, it goes the other direction. So it becomes alternating current. So the high transmission, power transmission line that comes from Niagara Falls by the hydroelectric plant, there the current that comes is alternating current. Namely, it goes from positive to negative, positive to negative, positive to negative, and those poor electrons, they actually are zipping down, back, zipping down and back, and zipping down and back. Whereas if you have it as a solar panel, then it is always only in a given direction. All right, so that's just so that we know the language. And here they just give some simple calculations of what is the current. And the current is a milliamp, and the amount of charge that flows across in 1 hour is 0.61 coulomb. I mean, you put in the numbers, these are just, and the current is milliamp, 0.17 milliamp, and you can figure out the energy. And this is now a conventional current. Is you have a device and is connected to a battery, and the engineers, electrical engineers, they have already adopted this convention that this longer line is positive and the shorter line is negative, and the current will flow from positive terminal through the device and come back this way. So the conventional current is this way, but the actual electron flow is the other way. All right, so this is just a picture to show us what we mean by a current. And now for these circuits, a big concept we need to sort of understand. Again, it is very important for our daily life. Is this thing called resistance. And this resistance is how much current will flow given the potential. Let's say the potential difference is 12 volts. And I now want to connect a, what is this? A torchlight. Yeah, a flashlight. If I connect a flashlight, then the flashlight will have some resistance. And it is a, what they call a filament in there, such that when a current flows, oh, this heats up. This filament heats up and gives off light. So that's the filament, and it heats up and it gives off light. And that's how when you now turn on your flashlight, you get light coming out. And this is now the resistance. And there is a law that says that the voltage across, whatever is the voltage across, due to this battery down here, the voltage across and the resistance, there's a proportionality. Namely, the more resistance there is, the smaller is the current. Given the voltage, V is equal to IR is this thing known as Ohm's law. We are all familiar with it. You must have already met with it in your high school. Voltage across whatever torch or lamp or device you have. Oh, the actual current that flows, given that the voltage is 15 volts, 12 volts, 110 volts, then the actual current that flows depends on what is the total resistance of your circuit. And in this case, the only circuit voltage, is this resistance, this filament. So then the actual current that flows is V over R. So V is equal to IR, or if you want to know what is I is V over R, and the unit is ohms. And I always like to download who is ohm. Well, ohm I guess, what is this? You know where's Nuremberg? Yeah, this poor guy, Ohm. He's German Austrian physicist, but he really did not have a he didn't have an easy life, let's put it this way. He was trained as first as a mathematician, engineer rather, and then he decided to study the physics of it. And when he discovered this Ohm's law in an article called The Galvanic Circuit Investigated Mathematically, when he presented that law, V equal to IR, it was coldly received. Namely, somehow people didn't trust his device because he had this galvanic device and the language was not yet clear in those days. So when he presented it, nobody took notice or did not say, whoa, right? And then his own college did not appreciate his work. And so he resigned from his position. Then he made an application to and was employed by Polytechnic School of Nuremberg. Well, that's not as famous a school as University of Munich. It's, I don't know, Polytechnic School of Nuremberg. Nuremberg is not such a big town in terms of science. And when Ohm arrived at, it took him in 1833, it took him how many years now? 18 years before he became a professor of physics at University of Munich. In other words, his stature was not recognized for such a long time, even though his work resulted in the Ohm's law. But today, everybody gives credit to Ohm's law, and Ohm has now the credit, but it took him a long time. So I guess the advice is, if you have a new invention and nobody seems to care, but if invention indeed is good, persist, don't give up. This guy, he was employed at this Polytechnic School of Nuremberg. He didn't resign. He resigned from the original one, but he stayed at Polytechnic School of Nuremberg and continued his research for 18 years before it became so well known that University of Munich says, "Woo, please come," right? So he was. All right. So we have already seen this Ohm's law, and you can give the flashlight and you can get the answer for whatever's the thing. And now, before we end, there is a question of what you call resistivity. Namely, if I have a wire, the longer the wire, the bigger the resistance, isn't it? You give me a wire, the wire will have some resistance, and the longer the wire is, the higher the resistance, and this resistivity is therefore a measure of the material that you have, because the longer the thing, the bigger it will be a resistance, and the smaller the cross-sectional area, the bigger the resistance. So you want to now measure this resistivity, and this resistivity now is this proportionality, how the resistance of the wire depends on the length and on the cross-sectional area. And the engineers would have measured, and they tell you for aluminum resistivity is this, for copper it is that. And when they now say, what wire should I use for transmission wire, they want to then use the kind of material where the resistivity is small. Why? Because the wire is over hundreds of miles. When you now have wire over hundreds of miles, you want the resistivity to be small, and you want now the cross-sectional area to be thicker. So when you have a high transmission wire, you can see that it is actually quite thick. It's not like like a thin hair, like a thread. It is a thick wire, and you leave it to the experts to figure out what to use, and they will then say, well, for longer extension cords, what you should use, and so on. So we'll leave it to, it is now 6:40, so we will leave it at this point, and we'll come back. We will have a class on Wednesday. We will have a class on Wednesday at 5 o'clock. Meanwhile, the GH, you will have a lab session, and Gabriel Legendre will be there at 6:50. Okay? Any questions? I will now Okay, so see you on Wednesday. Take care. Bye. If you have questions, you can email me and I'll answer them. Okay. Oh, I should stop recording.